I'm Daniel Finley with the Institute for Transportation Research and Education at NC State University. I'm going to discuss the use of the parabolic equation for vertical curves on a roadway. I'll cover the basics of vertical curves, how the parabolic equation fits into the design of vertical curves, and then we'll go over an example to illustrate these concepts. Vertical curves are used to provide a smooth transition from one grade to another. The tangents represent grades which can either be flat, uphill, or downhill. The typical vertical curve is a symmetric parabolic curve whose shape is defined by the parabolic equation. The information required to fully define a vertical curve is the elevation of the beginning of the curve, the grades of the two tangents that are connected, and the length of the curve. The entrance grade is known as G1 and the exit grade is known as G2. A vertical curve is depicted in a diagram such as this, a section through the center line of the road shown in the profile view. The horizontal stationing axis remains on a plane. That is, station points do not follow the elevated or depressed center line, and distances are measured in horizontal distances. This graphic shows the profile view of a vertical alignment and illustrates the path that a vehicle would take when driving along this alignment. There are two general types of curves, a crest curve that has a concave down shape and a sag curve which has a concave up shape. For a symmetric parabolic curve, the length of the curve is evenly divided on each side of the PVI. In other words, the distance from the PVC to the PVI is half of the length of the curve, and the distance from the PVI to the PVT is also half of the length of the curve. The term A represents the algebraic difference in grades of G1 and G2. The PVI is the point of vertical intersection, the point where the two tangents meet. The PVC is the point of vertical curvature, the point at which the curve begins. The PVT is the point of vertical tangency, the point at which the curve ends. The term X is used to denote any horizontal distance along the curve. We will use X to calculate the elevation of the curve at a point. X is bounded by 0 and the length of the curve. The letter Y is used to denote the elevation of a point along the curve at the distance x. An important note is that the grades G1 and G2 are measured in percent, and the distances x and L are measured in stations, where one station equals 100 feet. This terminology will become meaningful when we start the calculations. Mathematically, any point on a parabolic curve can be described using the equation y equals ax squared plus bx plus c. In the general parabolic equation, a and b are constants that determine the shape of the curve, and c is the y-intercept value, or the location where the curve passes through the y-axis. When we apply this to vertical curves, c is the elevation at the PVC. Therefore, if we know the equation and the distance x from the PVC, we can calculate the elevation of any point on the vertical curve. To customize the parabolic equation for finding the elevation of any point along a vertical curve, the term A is equal to G2 minus G1 divided by 2 times the length of the curve. The B term is equal to the grade of G1, and the C term is the elevation of the PVC. Again, all distances must be input in stations and grades in percent. This example shows two perspectives, a street level view in the top portion of the screen and the vertical alignment on the bottom of the screen, which takes a profile perspective. With just a few pieces of information, we can develop a comprehensive understanding of this curve. This information includes the elevation of the PVC, shown as 0.2 on the diagram, the entrance and exit grades, and the horizontal length of the curve. The entrance tangent runs from 0.1 to 0.2 with a grade of 4.8%, which is defined as negative 4.8% since it is a downhill grade. The road begins to curve at 0.2 and ends at 0.3 after a horizontal length of 550 feet, where it encounters the exit tangent with a grade of 3.2%. To develop the parabolic equation that defines the shape of this particular curve, we need to calculate A, B, and C. A is equal to G2 minus G1 divided by 2 times the length of the curve, or in this case, 3.2 minus negative 4.8 divided by 2 times 5.5, which is equal to 0.7273. B equals G1, or negative 4.8, and C equals the PVC elevation of 117.68. Therefore, our parabolic equation is y equals 0.7273 times x squared plus negative 4.8 times x plus 117.68. As an example, let's assume that we want to find the elevation of a point on the curve that is 270 feet from the PVC. 270 feet is equivalent to 2.7 stations, so we should input 2.7 for x. After plugging in our value, we find an elevation of 110.02 feet at the distance of 270 feet from the PVC. It is important to note that this equation is only appropriate for determining the elevation of points that are along the curve. Therefore, x values should only range from 0 to 5.5 stations. For elevations at points along the roadway outside of the curve, a geometric relationship between the distance and the grade of the tangents can be used to determine elevations. Thank you for your interest in this topic. Examples of vertical alignment exist on roadways all around us. I hope this presentation has helped you understand the basics of vertical alignment and vertical curve design.